shows the change in temperature, heat. You could picture as solid in the solid one here at the lower left. It raises in temperature as heat is added. Once it reaches the melting point at 0 degrees Celsius, the temperature does not change as it is added. It goes into breaking down the solid water into a liquid form, breaking apart those attractive forces between the water molecules. Once it's all liquid, then the temperature begins to raise again until it gets to the boiling point as heat is added. But at the boiling point, again, the temperature does not change. It stays constant at 100 degrees Celsius until the molecules have been separated into the gas form, and added does not change the temperature until it again returns to steam. So now again the heat increases the temperature. So the points here where the temperature is constant, these are called the phase changes, and at these points we have an equation that we use to calculate the amount of energy that's being put into the substance, and that equation is Q. Q will represent heat. Q equals the mass, M is mass, times a constant called the heat of fusion or vaporization. Fusion slash vaporization. And so this is a constant. So at the melting point, it's the heat of fusion, and at the boiling point, it's the heat of vaporization. So it'd be Q equals the mass times the change in the heat and vaporization. So we multiply by this constant. That's a simple way to calculate the heat involved in these phase changes. So we can figure out the amount of heat it takes to melt water, or likewise the heat lost when it freezes, or the heat it takes to boil water, to vaporize, that is, or likewise the heat that's lost when it condenses back to a liquid. So let's take a look at a few heat of fusion problems. So heat of fusion problems, that means we're at this point. We're looking at the amount of heat it takes to melt something or freeze something. How many kilojoules are required to melt a 10-gram popsicle at 0 degrees Celsius? Assume the popsicle has the same heat of fusion as water. So for this question, we'll need to identify our given values, of course. So we have 10 grams for the mass. Then we have the temperature given to us, 0 degrees Celsius. And it says the heat of fusion is the same as that of water. So we might need to look that up in a heat of fusion of water is 334 joules per gram. So delta H fusion, 334 joules per gram. Now the 0 degrees Celsius value, that is just there to show us that we're at the melting point. So we don't really need to do anything with that number. It doesn't plug into the equation. So these are simple problems where we simply just plug into the equation. Q equals the mass times the heat of fusion. And so it's just kind of a plug and chug problem. Plug in those numbers. The mass goes in for M, and the heat of fusion we substitute there, and we multiply those, and so we have 3,340, the grams would cancel out, since grams are on the bottom here and grams are on the top right there. And so the unit left over is joules. Alright, so the second problem is similar. It says grams of ice at 0 degrees Celsius will melt if 2.25 kilojoules of heat are added. So Q, 2.25 kilojoules. And we want to know mass this time. We know that it's at 0 degrees Celsius. But once again, that is there just to show us that we're at this point here, at the melting point. And one of the things we're going to need is the heat of fusion. So this is water. Delta H of fusion is 334 joules per gram. So our then is Q, the mass times the heat of fusion. This time we're solving for the mass. So the mass then, just rearrange it algebraically, the mass is Q divided by the heat of fusion. So now we can substitute our you might notice that our value for Q is not in joules. So let's take a look at what happens as it is right now. So mass is Q, 25 kilojoules over the heat of fusion, 334 joules per gram. So right now, as it is, kilojoules and joules will not cancel out. So this is one reason why it's important to keep units in the problem. We need to check to make sure these units are going to cancel out. So we could fix this, and we could convert our value of kilojoules into joules. So 2.25 kilojoules. For every 1 kilojoule, there's 1,000 multiplied by 1,000, and so the number of joules would be 2,250 joules. So we can use that number instead. So the mass then is 250 joules divided by 334 joules per gram. Now joules will cancel out the way they are supposed to. Alright, so we just calculate. And so that comes out to 6.74. Alright. Now, this last problem says in a freezer, 125 grams of water at 0 degrees Celsius is placed in an ice cube tray. How much heat and calories must be removed to form ice cubes at 0 degrees Celsius? So the mass, 125 grams. The temperature does factor in to know heat, but we want to know it in calories this time. And again, delta H of fusion is the same value, but we could use 334 joules per gram, but since we want our answer in calories, why don't we use a value in calorie times? We have more than one value for the heat of fusion, so that might make things slightly easier. Otherwise, I suppose we could just convert it. So it's 334 joules per gram. You could also convert that to calories. So, or to calories. So let's go ahead and convert that first. 334 joules converted to calories. The quality is 4.184 joules every 1 calorie. So we need to divide by 4.184. So that comes out to 79.8 calories. And so that'd be calories per gram. Alright, so now we just solve the problem as before. So it's Q, the mass. Q equals the mass times the heat of fusion. So the mass then is 125 grams multiplied 79.8 calories per gram. And so that comes out to 9,980 calories. Let's look at the next type of problem. So next we have heat of vaporization problems. Okay, so it says how much heat in calories is absorbed when 28.8 grams of liquid water at 100 degrees Celsius and 101.3 kilopascals is converted to steam at 100 degrees. So we have the heat as the unknown. Q is unknown, and in calories. The mass is 24.8 grams. And the temperature is 100 degrees Celsius, and the pressure is 101.3 kilopascals, and it remains at 100 degrees Celsius. So there is no temperature. There is no temperature change. We're dealing with this point right here. It's at 100 degrees Celsius. It starts at 100 and remains at 100 degrees Celsius. So we're using this equation. Looks essentially the same as the other equation. The mass is multiplied by the heat of vaporization. So we just need to use that value, the heat of vaporization. Now we have this information here, pressure. Do we need that? No, we don't need pressure. That's extra information. So let's just get rid of that. We don't really need to factor temperature into the equation. That's just there to let us know we're at the boiling point. So the equation Q equals the mass times the heat of vaporization. We need that value, the heat of vaporization, delta H of vaporization. And my reference here gives us that in joules, 2,260 joules per gram. So we can go ahead and use that value. So Q then is the mass, which is 24.8 grams, multiplied by the heat of vaporization, 2,260 joules per gram. Alright, so that comes out to 5,604 joules, which I'm going to round to. Q equals 5,600 joules. Now the problem wanted the answer in calories. So note here, problem wanted the answer in calories. So we need to do a conversion. Let's take our answer here, and we'll convert that to calories. So, there's 4.84 joules for every 1 calorie, and So that gives us, that's going to round to 1,340 calories. Okay, and that's actually our final answer here. Now, these heat of vaporization problems, you notice, are essentially the exact same thing as the heat of fusion. Okay, the only difference is we're at the boiling point rather than the melting point. So let's go ahead and let's look at another type of problem now. And let's look at the combination of several different types of heat calculations. So we're going to combine, or we're combining heat calculations. So this problem says, how many kilojoules are released when 75 grams of steam at 100 degrees Celsius condenses, cools to 0 degrees Celsius, and freezes? So we're combining several calculations here. So we are starting off looking at our diagram. We're starting off with steam at 100 degrees Celsius. So on this diagram, that's going to be right here. Steam at 100 degrees Celsius. Now it condenses and it cools to 0 degrees Celsius and completely freezes. So it condenses, it goes through this phase change all the way, so it condenses all the way, then it cools all the way to 0 degrees Celsius, and then it completely freezes at 0 degrees Celsius. So it starts here, this is the initial, and it ends right here. This is the final. So, or we could mark letters, initial and final. So it starts here and ends here. Now, we have the equations for the phase changes, but what about this point? How do we figure out the temperature here? Well, this is an equation that we've already dealt with earlier. And so this is the equation. Q, the heat, is the mass times the specific heat times the change in temperature. So the heat is the mass times the specific heat times the change in temperature. Notice that this equation has a place for the change in temperature because temperature changes at this point. Temperature does not change at these other points, so there is no place to factor in the change in temperature. So basically we're going to have to find the heat at this point, then we'll add that to the heat at this point, and then we'll add that to the heat at this point. So let's write down our information. So we want to know the total kilojoules. And we have a mass of 75 grams. And it starts at 100 degrees Celsius, will end at 0. But we're going to need the heat of vaporization, which is 2,260 joules per gram for water. And the heat of fusion, which is, just wrote that down a second ago, let me double check that, 334 joules per gram. And then we also need the specific water, so 4.184 joules per gram degrees Celsius. Alright, so using all those things, we're going to add it all up. So we have, let's call this Q1, we'll call this Q2, and we'll call this Q3. Q1 will be the first phase change of the gas condensing. Q2 will be the temperature change of the liquid water cooling, and Q3 will be the final phase change of the ice freezing, ice forming. So Q1 so Q1 then is going to be the mass times the negative multiplied by the negative heat of vaporization. And it's negative because actually the heat of condensation value that we're using, it's when it's going down, the negative number is used to show that the heat is being released. So just a reference point, really. If the temperature, if the heat was going in the other direction, if we were going to the right, if the steam was forming rather than condensing, if it was vaporizing rather than condensing, positive sign. All right, so this first Q1 we calculate, and so the mass is 75.0 grams multiplied by the negative value to negative 2,260 joules per gram. All right, and that comes out to 170,000 joules. Then Q2, that's this one. We're going to find that by doing the mass times the specific heat times the change in temperature. So the mass, again 75.0 grams, is multiplied by the specific heat, which is 4.184 joules per gram degrees Celsius, which is then multiplied by the change in temperature. It's going from positive 100 to 0, which is negative 100 degrees Celsius change. So the change again is a negative because it's going, temperature's going down. All right, so we solve for Q2 now. And so that's going to give us negative 400, 30,400 joules. You know, and I forgot to put the negative sign on this number right here. That one should be a negative as well. All right, and the last thing, last value, Q3. So again, we're using this equation. And so Q3 is the mass times the negative heat of fusion. So I guess this should have parentheses. Both of these here should have parentheses. So we're multiplying the mass times the diffusion, and so that's going to be the mass, again 75.0 grams, multiplied by 334 joules per gram. And so we calculate that. Q3 then is 25,100 joules. Okay, so now we just need to add up Q1 plus Q2 plus Q3. So we find the total temperature, Q total I'll call it, is Q1 plus Q2 plus Q3. Add those up. Q1, which is negative 170, joules plus negative 31,400 joules plus negative 25,100 joules. The negative sign on that one as well. So those all should be negative values. Q3 is also negative. All right, so we just add those numbers up. And so total temperature comes out to total energy change, heat change, and I'll need to round that number. So, and we also need to convert that to kilojoules. The problem said to report it in kilojoules, so there are 1,000 joules in every kilojoule. And so divide by 1,000 and round. Total temperature change is negative 3 sig figs, so 227,000. So 200, negative 227 kilojoules. All right. So that's a process when we have multiple heat equations that we are combining.